Meet Cryoconite, the dirty ice that eats sunlight. Dark specks turning pristine glaciers into heat sponges, accelerating melt in unexpected ways. Cryoconite forms from wind-blown dust, soot, volcanic ash, and microbes clustering on snow, creating dark aggregates that dramatically lower surface brightness. Microbial communities colonize these grains. Cyanobacteria produce pigments and sticky polymers, deepening color, binding particles, and trapping even more absorbing material. Sun-warmed clusters melt tiny pits called cryoconite holes, miniature ponds hosting microbes, sediments, and bubbles, thriving atop seemingly lifeless ice. Where do particles originate? Deserts, wildfires, industry, and volcanoes loft aerosols globally, eventually settling onto polar and alpine ice surfaces. On snow, wind concentrates dark grains into hollows. Solar heating melts films, gluing particles together and helping them resist blowaway. Cyanobacteria exude extracellular polymers, natural glue, binding minerals into pellets. Their dark pigments capture light, powering photosynthesis in freezing conditions. Pellet size, shape, and porosity control sinking and heating. The darker the mix, the lower the albedo, the faster localized melt. Albedo is reflectivity. Fresh snow reflects sunlight. Cryoconite absorbs it, converting light to heat and kickstarting a powerful positive feedback loop. As pellets warm, they melt downward, drilling cryoconite holes until water depth equalizes heating and cooling, suspending the sediment at equilibrium. Winter snowfall buries and brightens surfaces, spring melt exposes dark patches, summer sun expands holes, merging into networks of low albedo zones. Meltwater concentrates along streams, routing heat and sediment into crevasses, reaching the bed and influencing flow through lubrication and channel evolution. From Greenland to the Himalaya and Alps, black carbon and dust amplify melt. Satellites and drones map darkening patterns across ice sheets. Warming raises dust and wildfire emissions, boosting cryoconite loads. More absorption means more melt, exposing more dust, a reinforcing climate feedback. Researchers sample holes with sterile tools, sequence DNA, measure spectra, and deploy time-lapse cameras to understand biology, optics, and melt dynamics. Reducing soot and dust emissions can limit darkening. Meanwhile, Cryoconite reminds us Earth's coldest places harbor resilient, surprising ecosystems worth protecting.